Welcome back to the workshop. We want to take a look at section 3 of the appendix again. So we've already taken a look at a couple of examples of direct proofs, and here we want to take a look at another direct proof, but what we're going to have is we're going to have cases in this proof. So what exactly do I mean by that? Well, let's take a look at our example to see. So in our example, we're looking at if m and n are integers, or we're supposing that they are, if m and n are of the same parity, then 3m plus n is even. Well, of course, if you don't know what parity is, we have a little bit of a problem, and that's okay, right? I don't expect you to know. So what is parity? Well, parity refers to a number being even or odd. So when we say that two numbers are of the same parity, then either both of them are even or both of them are odd. Okay, so when m and n are both even, then 3m plus n is even. Also, when m and n are odd, then 3m plus n is even. So the two cases that we get, right, we have two situations, either they're both even or they're both odd. So we get two cases, they're both even or they're both odd. And it's very difficult to consider these at once, right? We have representations for even and odd, so we can utilize those to show that 3m plus n is even or odd. But to do that, we need to show that, use those definitions for m and n themselves as well. And to do that, right, we have to say, hey, let's look at when they're both even, and hey, let's look at when they're both odd. But those are two different situations. They're two different cases. So we just want to consider those two things because they're both involved in this one statement. And that's all that we really mean for cases, when we have multiple situations within one statement. So proof. What does it look like to have a proof with cases? Well, again, let's take a look. Let m and n be integers. All right, and we want to assume the premise is true. So we want to assume that m and n are of the same parity. So once we know that they're of the same parity, again, we end up with the two cases. We end up with case one. Case one is that both m and n are even. So the other case would be that both m and n are odd. So case one, both m and n are even. Then, right, since m is even, we can write it in one particular way, and since n is even, we can write it in one particular way. So we get that m is 2k, can be written as 2 times k for some integer k. And n can be written similarly, 2 times l. Why l? L because we don't want it to be k. We don't. If m and n are the same number, then they would both be equal to 2k. But m and n, we don't know that they're the same number, so we have to represent them differently. So this is for some integer l. Excellent. Then we have that 3m plus n can be written as, let's see here, we have 3 times m, which is 2k, plus n, which is 2l. So again, we have some assumptions about m and n. In this case, they're both of the same parity. And more specifically, we're looking at when they're both even. So we have representations for them. Now that we have utilized that definition, we want to try and show something about 3m plus n. In particular, we want to show that it is even. So in order to do that, I need to be able to write it as 2 times something. Okay, so I have to look at what 3m plus n is. Well, I recognize that I can write m and n as 2 times something since they are both even, which gives me, pull a common factor of 2 from both of these terms, gives me 2 times 3k plus L. Immediate, right? And then since 3k plus L is an integer, 3m plus n is 2 times an integer, and 3m plus n is even. Excellent. So that takes care of case 1. When I have that they're both even, then I get that the conclusion is true. In case number 2, I have, again, that m and n are of the same parity. So we have that both m and n are odd. Right, I've got 2 situations. They're both even or they're both odd. So I'm looking at the second case where they are both odd. Then, now you can, for those of you that are maybe computer science folk, or you've taken a computer science class, we can think of k and l as locally defined variables. So once we're done using k and l here and we begin a new case, the definitions for k and l go away. So we can reuse k and l for case number 2, but if you didn't like that, you could use p and q instead, for example. I'm going to reuse k and l because, right, I'm done using them here. I can consider them something new, right, because I'm considering a different, right, a different scenario for m and n. So if they're both odd, then I can write m as 2k plus 1 for some integer k, and I can write n as 2l plus 1 for some integer l. Again, you could use p and q here if you didn't like that they were the same. And that would be fine. So once we have that, again, we have applied the definitions of odd to m and n. So let's go ahead and see what these definitions give us when we look at 3m plus n, because we want to show that 3m plus n is in fact even still. Okay, so let's give this a shot. M is 2k plus 1, so this is 3 times 2k plus 1, plus n is 2l plus 1. All right, so this gives me 3 times 2k, which is 6k. 3 times 1 is 3, plus 1 is 4, and I still have the 2l. So I have 6k plus 2l plus 4. So you could write that out in several steps. I'm writing out in one. Either way is fine, right? This isn't an algebra course. This is a proof writing, at least section in our course. So I'm not worried about you showing all of the steps, but you should show some. So here I'm showing some. I can pull a common factor of 2 out, and I'm left with 3k plus l plus 2. And once I have that, then I can say since 3k plus l plus 2 is an integer, I have that 3m plus n is even, since it is written as 2 times an integer. Okay. Therefore, right, so now I've shown that for every possible scenario, both even, both odd bits, every possible scenario. So for every possible scenario, I have that 3m plus n is even. So therefore, if m and n are of the same parity, then 3m plus n is even. because it doesn't matter which scenario I'm looking at, I always get that 3m plus n is even. The only bit here that might be tricky at times is determining all the possible cases. Okay, you might not even recognize that you need cases right at first, but then when you go to manipulate something, you say, I don't know something about this. Well, could you split it up into cases and then say these are the only possibilities? And that might be the way to go about it. Okay, so in this case, cases. But this is the restatement of the implication that we wanted to prove, right? We showed, again, trying to show what we've got here. We assume the premise, and then we end up with cases. And for both of the cases, we do some work, and we get that Q is true. Q is true there, Q is true here. But for all of the cases, we get that Q is true. Therefore, we can conclude that the implication is true. And of course, don't forget to indicate the end of your proof. Since we were able to prove it and we're done, we indicate the end of the proof. All right. So that is an example of a proof, a direct proof that requires cases. In our next video, we'll take a look at proof by contraposition. So we'll see that next. I'll see you guys back in the workshop very shortly.